Welcome everyone, Adam LaFaccia, your moderator, rejoining you, and thank you so much for joining us for today's session, part of the Smithsonian Online Education Conference series, and today's session is How Things Fly. Now before we get started, I'm just going to cover a few technical aspects of the online room with you. First off, you'll notice that there's a questions or comments box on the left side of the screen, and you can use that box to enter in your comments and questions throughout the session today. Now, if you have any technical questions, you can type them in there and I'll respond to you privately to get those sorted out with you as quickly as possible. But if you have any content-related questions, we'll be holding those for different Q&A periods along the way. So if you don't get an immediate response, don't worry. We are also joined by multiple educators and explainers joining us from NASM, the National Air and Space Museum. And you'll see that they'll type some responses to you in the chat since we probably won't have time to answer all of the questions that come in today. If for any reason you have a larger technical issue and you're not able to contact me for assistance, you can email us at smithsonian@learningtimes.com and our team will work with you to get you signed back into the online room as quickly as possible. You'll also notice that we're providing live closed captioning for the session today at the bottom of the screen. If for any reason you find that distracting, you can click on the drop-down menu and change it to no captions, but we hope that you find it a useful tool today. The conversation today isn't just limited to the online room. We also hope that you'll continue to engage with us, both with Smithsonian Quests and shareable Smithsonian Education badges, and you'll see there's a website on the screen where you can find more information about those. And I'll also be turning the floor over to Ashley Naranjo from the Smithsonian in a little bit to talk more in depth about the quests that are available for today. But we're also connecting with everyone in the Twitterverse, so feel free to tweet with us with hashtag HowThingsFly. And with that, I'm going to turn the floor over to Ashley Naranjo.
Thanks so much, Adam. This session is actually part of a larger series, so there's plenty of archived sessions available for you at smithsonianeducationconferences.org. You probably saw that when you were registering. In addition, each conference session has an accompanying digital badge, and today we're very excited to share with you the Aviator ACE, which is 4 quest activities that explore the design of a plane, how best to construct a paper airplane, and allow students to try new experiments to learn about propulsion and Bernoulli's principle. We're also very excited to share with you a long-term collaboration that we've had with the Pearson Foundation, who helped us create short 4-minute videos, films available on YouTube called Explore with Smithsonian Experts. And we're glad to share that Dr. Anderson is actually featured in one of these video films that talks about the Wright brothers and their experimentation process and the importance of documentation in this process. We also have one that features the natural history entomologist Dan Babbitt, and you'll see him on the screen with the multiple stages of insects. And here tomorrow, actually, with our friends from the National Museum of Natural History and the Curious Education Center, they'll also be holding a live webcast at 11 a.m. and 2 p.m. And we teamed up with them to create the Arthropod Agent, which is another digital badge opportunity for students where students can identify and protect insects in their own community.
Wonderful, and thank you so much, Ashley. That means we are now ready to launch into How Things Fly, and I promise no pun intended there, as we turn things over to Dr. John Anderson and Michael Hulslander, both joining us from the National Air and Space Museum. Thank you for joining us today.
Thanks, Adam. Thanks, Ashley. This is Mike Hulslander, and as Adam said, I'm with the National Air and Space Museum. And I thought before we take off talking about misconception in flight, pun intended there, I think everyone might like to learn a little more about both Dr. Anderson and myself. So, Dr. Anderson, if you don't mind, let's start with you. You originally studied and worked as an aeronautical engineer, correct?
That's right, Mike. In fact, I'm sitting here with Mike. I am currently the Curator of Aerodynamics at the National Air and Space Museum. I'm a retired professor of aerospace engineering from the University of Maryland at College Park. And this subject is you're going to find, I hope, very interesting. The whole idea of flight is challenging to understand and wonderful to learn about.
Great, thanks, Dr. Anderson. Now, I'm assuming something got you interested in aeronautics. Can you tell us a little bit about, your interests as a younger person and why you got involved in aeronautical engineering?
Oh, absolutely. I built model airplanes starting when I was about 5th grade. And I built model airplanes because I love the aesthetic beauty of aircraft. When you think about it, when you look at airplanes, many of them are just beautiful works of art. So I started building model airplanes and have been building them ever since. And believe it or not, as strange as that may seem, that was the real motivation for me ultimately to become an aeronautical engineer and an aerospace engineer, to be able to learn how these airplanes actually work.
You've also written a number of books and taught on various topics related to aerodynamics. Many of your books are used in colleges around the country to teach undergraduate students in aeronautical engineering. So can you talk a little bit about how other companies come to you for advice and for teaching?
Well, if you live long enough in working in what you do for your profession, you become known by other people in the profession, and sometimes they feel that you can be a help to them, either in terms of teaching or in terms of research and the technology. And so after a long while, and you become integrated into the field the professional field of aerospace engineering.
Okay. Thank you, Dr. Anderson. Now a little bit about myself. I think it's okay to say that I've always loved science. I built aircraft models as a young child and did a lot of drawing of aircraft as well. When I was in school, I took a lot of science and math classes, and I just happened to fall into the museum education field. In fact, when I was going to school studying science and math, I had no idea that I could pursue a science education career in the museum setting. I started my informal science education career as a high school explainer, and we do have some explainers that are listening to this online conference, but I started just like them in a zoo in my hometown, educating visitors about the animals in our zoo. And as I got older, I found that I really enjoyed sharing that love of science and engaging with people who came to the zoo or the museums I was working at. So I decided to go into a career of museum education. And for the past 25 years or so, I've been a science educator at both museums and zoos. And obviously now I'm with the National Air and Space Museum as the manager of on-site learning. And basically that means I'm in charge of our learning centers in the museum as well as the explainers program. And I specialize in science programming at the museum. So I help write a lot of the science education programming we do there. Anyway, enough about us. Are you ready to move on to misconceptions in flight, Dr. Anderson?
Yes.
Okay, so let's get started and go to the next slide. We have a poll question for you. And so this online conference is about misconceptions in flight. So I want to make sure that everybody knows what a misconception is. So if you could just look at that poll and answer the question.
Great, and you'll all notice that you can click a gray bubble that corresponds to your answer there, and we'd love to see what you think. Looks like our second option, it's an incorrect opinion based on faulty thinking, has been maintaining a solid lead.
Well, that's great because that is the correct answer. B is the correct answer. A misconception is a view or an opinion that is incorrect because it's based on faulty thinking or understanding. So we're going to take a look at several misconceptions related to two specific issues here. But let's give an example of a misconception. So you see that there on your screen now. Perfect eyesight is required to be a pilot. That is actually a misconception. How many, let's do a poll question before we move on. You'll see that again on your screen.
Great, and we'd love to know if you'd like to know how to fly an airplane. And it looks like, once again, a strong lead coming in here, this time on yes.
Oh, that's great. So you're in the right place, I guess. So the misconception, perfect eyesight is required to be a pilot, is not quite accurate. As long as your vision can be corrected to 20/20 with glasses or contacts or surgery, you are eligible for a first-class FAA medical certificate, which allows you to fly as a civilian professional pilot. Military requirements are much more restrictive, though, so you would need that 20/20 eyesight for military aviation. All right, so let's move on to the forces of flight. I want to start off by doing another poll question. And I want to see if everybody knows what a force is.
Great, and you'll see a number of options right there on the screen again, so feel free to click on those. And it looks like, ooh, it's shifting quite rapidly, actually. We started off with a lot of people voting it's the property of matter that causes it to have inertia, and now it's shifting much more heavily to it's a push or pull on an object in a specific direction.
Okay, great. We're getting almost 100% on that answer, and you all would be correct. We have a smart bunch here. Yes, a force is any influence like a push or a pull, which tends to change the motion of an object in a specific direction. So before we talk about all of the forces of flight, let's find out if everybody knows what forces affect things flying in Earth's atmosphere.
Great, and you'll notice actually in this poll you can click more than one answer, so just a little bit of a hint, there's probably more than one that's correct.
Okay, yeah. Most everybody has pressed all of the above, and you would be correct. The four forces of flight that affect everything flying in Earth's atmosphere are lift, weight, drag, and thrust. Basically, when an airplane flies, the wing is designed to provide enough lift to overcome the airplane's weight, while the engine provides enough thrust to overcome drag and move the airplane forward. So let's take a look at the four forces of flight. There you can see them. They're pointing in the directions in which the forces push or pull. All right. Now let's talk about one of the four forces, that is lift. What is lift? Lift is the force that acts at a right angle to the direction of the motion through the air. Lift is created by a difference in air pressure for aircraft. One of the first misconceptions we're going to talk about relates to the misconception of how lift is generated. So misconception number one, equal transit time. This first misconception, you might have also heard of it called the longer path theory. So let's do a poll question. This one asks, have you ever heard of the equal transit time theory?
So it looks like the majority are saying no, but is that from Star Wars is keeping pace with yes?
I think once you hear the explanation of equal transit time theory, you might change your answer. I don't know if we want to redo the poll, but this first theory was one I was originally taught in school many years ago, and I've actually seen the same explanation used in several textbooks that are still in print today. You can also find this explanation for the generation of lift, that is the equal transit time, all over the internet. So, Dr. Anderson, maybe you can explain to the folks what the equal transit time theory is, and does this really happen as air flows over a wing?
Okay. First of all, what's transit time? Transit time is the time required for something or somebody to move from one point to another. So the equal transit time theory, which is a misconception, is this sort of thing. What you see on the screen in this black area, that's an airfoil. It's a section of a wing, for example, on an airplane. And these dotted lines are the motion of little elements of air moving along in the flow over the wing. First over the top, and this one is a flow over the bottom of the airfoil. Now, intuition might tell you that when a hunk of air gets up here to the front of the airfoil, it's called the leading edge, that it would divide, and part of it would flow over the top, and part of it would flow over the bottom. And intuition might tell you that the part that's flowing over the top has to arrive at the edge of the airfoil at the same time that the flow over the bottom arrives. That's the equal transit time theory, that flow over the top and over the bottom have an equal time to flow over the surface of the airfoil, meeting at the trailing edge. And that would say, well, since the airfoil is curved on the top, there's a further, longer distance for the flow to travel over, and that would say, my goodness, that flow over the top has got to be moving faster than the flow over the bottom to get to the trailing edge. That's a misconception. In reality, let's assume that you are a hunk of air, and you are flowing along this little path, call it a streamline, over the top. You will, given a certain period of time, get down to this location, and it's downstream, it's behind the airfoil. If you are also a hunk of air flowing over the bottom surface of the airfoil, in that same amount of time, you will only arrive at that location. So on the bottom, you're arriving at that location, flowing over the top, you actually arrive at this location much further downstream. And that debunks. This is based on real calculations, real experiments, and that debunks the equal transit time theory, the misconception.
You know, and one question that popped in while you were speaking there, and I'm hoping you can clarify, what exactly is an airfoil?
Yeah, what is an airfoil? Most of you can imagine a wing, let's say a wing of an airplane, and the wing of the airplane is moving forward. And let's say that you take a plane or a razor blade and slice the wing in the direction of motion of the airplane. The cross section of the wing that you see is called the airfoil shape. It's literally, the wing is made up of, you might envision a whole series of different airfoil shapes placed side by side, making up the wing. The airfoil shape is what you see if you slice the wing perpendicular to the wing, but moving in the direction of the airplane. It's kind of easy to see an airfoil shape.
Yeah, you might understand it if you compare it to a loaf of bread. An airfoil is a cross section of wing, just as a slice of bread is a cross section of a loaf of bread.
Good comparison.
Okay, so let's move on to misconception number 2, momentum. The momentum theory isn't as well known, nearly as well known as the equal transit time theory, but what exactly or how does this explain lift?
Well, if we go to the next picture, do we have? Oh, there we go. What you have here is a diagram of flow over an airfoil or over a wing. These lines are the lines of streamlines of the flow. This white arrow illustrates the lift on the wing, the generation of lift on the wing. And this sort of big black arrow down here shows that there's a general downward movement of the air behind the wing. Is called downwash. One explanation for lift is that the airfoil causes the air to deflect downward, and there is an equal and opposite reaction to that, which gives you the lift. Why this is a misconception, I mean, this happens, but why this is a misconception comes down to the words cause and effect. If you ask what the cause of lift is, that's due to a difference in pressure between the top and bottom surfaces. The effect of the generation of lift, however, since the air is pushing upward on the airfoil pushes downward on the air and causes the air to flow downward. So that's the momentum of the air being pushed down by the presence of the airfoil. The misconception is that this downward motion of the air down below the airfoil, that's causing the lift. That's not true. The cause of lift is the pressure difference between the top and bottom surfaces. And the fact that the air flows downward underneath the airfoil is the effect of the generation of lift. It's kind of an equal and opposite reaction. But it's the effect of it. It's not the cause of the lift. So really we're talking about almost semantics between the meaning of the word cause and the meaning of the word effect.
I see a great comment that popped in here from Ashley. Could you say an airplane in flight is always in the middle of a sort of tug of war with the four forces? Well, what are your thoughts on that kind of metaphor?
Mike, what do you think?
Absolutely. To increase speed of an aircraft, you would have to increase thrust or reduce drag somehow. And obviously, to increase altitude, you would either have to increase your ability to generate lift or decrease your weight, the weight of the aircraft. So yeah, it's a constant tug of war between the four forces of flight, I would say. Yes. Balancing and equaling them out.
Yes, yes, exactly.
Okay, let's move on, if we don't have any more questions, on the third misconception. The third misconception, circulation. This theory isn't that well known either. I actually didn't know about it until I came to work at the National Air and Space Museum. But as I've been told, it's one of the oldest misconceptions, but it is just as much a misconception as all of the others. So, Dr. Anderson, can you explain again what's going on in this theory and why it's not the cause of lift?
Well, let's visualize the airfoil again. There we go. In this picture, you see, first of all, let's look at the bottom. You see streamlines flowing over the airfoil. This is because the flow up ahead is moving from right to left. So the streamlines over the airfoil. Now, if indeed you were to visualize this flow as just straight parallel streamlines going straight like this, straight across, you wouldn't see these streamlines. To see these streamlines, however, if you took that straight parallel flow and add to it this little circulatory motion, it's called circulation. Then indeed, you might think, if you're adding this picture to just straight streamlines, you'll get this picture down here, and you do qualitatively. The idea of, first of all, circulation gives the misimpression that the airflow flows around the airfoil. That's not true at all. There is no airflow around the airfoil like this. The airflow flows over the airfoil like this. But there is a mathematical definition that is called circulation, and I don't think it is worthwhile for us to get into this mathematical definition. This mathematical definition involves something like this. Indeed, if we did have flow in a circle like this or a flow in a closed path like this, there would be something called mathematically circulation, which you can then add to the free stream here. And it gives rise to what's called the circulation theory of lift. And as a matter of fact, back about 1920, the early explanation finally for generation of lift was that you take the density of the airflow, the velocity of the airflow, and you multiply that by this mathematical thing called circulation. And as a mathematical theory, that gave rise to reasonable estimates and calculations of the lift on the airfoil. However, the misconception is the idea, well, with the circulation, the flow circles around the airfoil. That's not true. It doesn't do that. In essence, what we have here is the best you can say is that if you take a uniform flow, straight stream lines, add to it conceptually a picture like this, flow circulating around, up here at the top, that adds this velocity up here, adds to the flow down here and speeds up the flow over the surface. This, down on the bottom part of this circulation, the flow is going in the opposite direction from right to left. That detracts from the flow incoming the airfoil and slows the flow down. So you end up with qualitatively a faster flow over the top and a lower flow over the bottom. So qualitatively, the circulation theory lift is a way of looking at things. And quantitatively, mathematically, it gives you reasonable ways of calculating the lift. But without me, I'm going to use some words, and this blows you out of the water. Don't worry about it. But if you would take a fluid element, let's put it this way. If you would take a closed path around the airfoil like this, and you multiply at each point the flow velocity times the distance the little fluid element moves, and then you integrate that all the way around the airfoil. It doesn't have to be a circle or anything like this. You can integrate it around the airfoil. That integral, see, I'm using a word that you'll learn about in calculus, that integral of the velocity times the distance around a closed path around the airfoil, that is what mathematically is called circulation. And that's the thing that you multiply by the free stream velocity and the density of the air times the circulation, and that gives the lift mathematically. And that works. But it's an abstract thought in many respects. It's mainly a mathematical thought, although I've tried to indicate some general feeling of physical application here. But to say that circulation causes lift is a bit of a misconception. It's kind of stealing a mathematical concept called circulation, which you can then multiply by the density, multiply by the flow velocity to get the lift. That's called the Curator-Joukowsky theorem, by the way. See, I'm using terms that are blowing everybody out of the water.
It's
but
nice.
I want to use this intentionally to tell you why it's easy to have a misconception when you talk about the circulation as a misconception as the cause of lift. I think we just have to wait until you grow up, take an aerodynamics course, and learn some of the mathematics and the circulation, the theory of the circulation theory of lift. So in a way, the idea of circulation is not a misconception. But when you think in terms of applying it like the little fluid elements moving around in a circle around the airfoil. Boy, that's a misconception. That doesn't happen at all. The fluid elements move as shown down here in this picture.
Well, thank you for touching on a lot of those things that people can further explore after. I feel like we could spend an entire hour just breaking this down.
Absolutely. But some of those words were used for the aeronautical engineers listening in, so they would then, we have to be legal in terms of the aeronautical engineering.
Well, thank you.
Okay, thanks, Dr. Anderson. So, what's really happening here? How does a wing generate lift? We're going to take a look at what Jamila, an explainer at the Smithsonian National Air and Space Museum, has to say about lift.
Hi, my name's Jamila. I'm an explainer at the National Air and Space Museum's How Things Fly Gallery. And today I'm going to talk to you about lift. I'm standing in front of the Spirit of St. Louis airplane. It was flown in 1927 by Charles Lindbergh, and it was the first successful solo flight over the Atlantic Ocean. Now, how was this plane able to generate lift? How was it able to stay in the air? Now, I can explain that using this airfoil here. An airfoil is like a cutout or a cross-section of a wing. So if I were to take a wing and slice it into pieces like a loaf of bread, this would be one slice of the wing. Now, if we compare this airfoil to the Spirit of St. Louis, we'll notice they have very similar shapes. They have curved tops and flat bottoms. An airplane's wing will be shaped this way because of something called Bernoulli's principle. Daniel Bernoulli was a Swiss mathematician who studied the movement of fluids like air and water. And he realized that a faster moving fluid will have a lower pressure, while a slower moving fluid has a higher pressure. Now let's apply this to our airfoil or to a wing, so that when the plane starts flying and air hits the wing, you're going to get faster moving air on top. It's going to speed up because of the curve. At the bottom where it's flat, you're going to have a slower moving air. It's not going to be as fast as the air on top. That slower air is high air pressure, and the faster air is low air pressure. That high air pressure pushes up on the airfoil or up on the wing, and that's why something as heavy as an airplane can fly. Don't believe me? Well, I have an experiment we all can try at home with a single sheet of paper. If I were to place this paper beneath my lips and blow, would it go up or would it go down? Let's see what happens. We notice that the paper goes up. And the reason why is because of Bernoulli's principle. When I blew my fast air on top of the sheet of paper, it was a lower pressure than all of the air in the room, because the air in the room is slower than the air that I was blowing. So that high air pressure works from beneath and it pushes up on our sheet of paper. And the same thing is happening to an airplane's wing. And that's why something as heavy as an airplane, like the Spirit of St. Louis, is able to generate lift.
Okay, that was Jamila, and Jamila is an explainer at the National Air and Space Museum. We have another poll question for you. So when we're ready, we want to ask, have you ever flown a paper airplane before? Oh, okay. So quite a few of you have built and flown a paper airplane before. Good. So Dr. Anderson, Jamila's explanation of the generation of lift was pretty basic. Was there anything you would like to add to that?
I think it sort of stands by itself. In a few minutes, a little bit later on, we'll actually talk more about pressure, for example, exerted on the surface, and ultimately the pressure being different on different parts of the wing and the airplane gives rise to an aerodynamic force. But we'll talk about that later on.
Okay. Now our poll question for that, our last poll question was for paper airplanes. Can you explain briefly how something like a paper airplane that doesn't have a typical airfoil shape generates lift?
Oh yes. You don't have the shape of the airfoil. The shape of the wing is not the only factor that contributes to what the lift is. It's also the angle that the wing makes to the airflow. It's called angle of attack. And so as you increase the angle of attack, you get higher lift on the surface. Again, it doesn't have anything to do with the shape. Imagine a barn door. A barn door will produce lift if you fly it at a high enough angle of attack. Why don't we fly around on barn doors? Well, there's another aerodynamic force called drag that we have to be concerned about, and the aerodynamic drag on a barn door is humongous. So we don't fly around on barn doors. It's horribly inefficient. But anything really can produce lift if you put that any object, at some angle to the flow.
Okay, so with a paper airplane, that flat wing will generate lift,
yes,
if you have a high enough angle of attack and enough thrust.
Yes,
obviously.
Exactly.
Okay.
Exactly that.
So that leads us on to our next force of flight that we're going to discuss, and that is thrust. Thrust is the force that propels a flying machine in the direction of motion, and generally engines produce that thrust. Okay, Dr. Anderson, I think this misconception here is probably one of the biggest that we'll talk about today. And it's often used to explain thrust. In fact, again, you can find this explanation in quite a few textbooks and all over the internet. But does Newton's third law, can you use Newton's third law to explain, again, the cause of thrust?
Good question. I'd like for everybody to imagine a picture like you see on the screen here. We have, for example, a rocket engine. And let me bring this down here. There we go. You see, here's the rocket engine. Here's a nozzle. You see a high-speed blast of gases out the back end, out the exit of the nozzle. Anybody who's seen a rocket engine operating will know that, man, that is a really high-speed flow of gas out the back end. You will see the explanation given almost always that thrust on this rocket is produced by this high-speed jet of air going out the back end of the rocket engine. Well, think about that. This high-speed jet of air is going out the back of the engine. See where that green arrow is? It's down there. Now, how in the world can that high-speed jet of air down there have any effect on literally what's happening with the rocket engine? In reality, simplest way to look at this is that the fuel and oxidizer being burned inside the rocket chamber creates a high pressure. That pressure is exerted on the internal surface of the rocket engine. And it is this internal pressure inside the rocket engine that pushes the rocket forward. That is what is generating the thrust. Now, the jet of air back here is the equal and opposite reaction. There's Newton's third law. Because the rocket is being pushed forward by this pressure inside, then the gas inside, the gas itself, is pushed backward. That is the effect of the generation of thrust. So we have the jet of air, the equal and opposite reaction, but it is really not that jet of air that's creating the thrust itself. That's the effect of the generation of thrust. What's causing the thrust is the pressure distribution exerted on the interior surface of the rocket engine. And this is a misconception because you'll find the explanation I just gave you, you will not find that many places.
Okay. So let's take a look at some propulsion systems. Before we explain what's happening, maybe we should say something quickly about some of the more common propulsion systems that you might see in an aircraft. Generally, there are three kinds of engines that power most flying machines. There are piston engines, which you see in the upper left-hand corner of your screen, right there. You have jet engines, right over here on the upper right-hand side. And of course, rocket engines. And all of these propulsion systems basically depend on the same principles to produce thrust. First off, the engine mixes fuel with oxygen or another oxidizer in a combustion chamber. Then the mixture is ignited somehow. The burning mixture then creates hot, expanding gases. And eventually those expanding gases either produce thrust directly, like in a jet or a rocket engine, or they're used to push a piston or drive a turbine and connect it to a propeller. So what's really happening with the generation of thrust? How does an engine, like a piston or jet or rocket engine, generate thrust? Let's hear from Jamila, the explainer at the National Air and Space Museum, again to see what she has to say about thrust.
Hi, my name is Jamila. I'm an explainer at the National Air and Space Museum's How Things Fly gallery. And today I'm going to be talking to you about thrust. I'm standing in front of the Hughes H-1 airplane. This airplane was designed by Howard Hughes, and in 1935 it set a world record at the time for being the first plane to fly at speeds of up to 350 miles per hour. Now what I have here is called a propeller. A propeller is a form of thrust. Let's see how it works. What made that propeller fly out of my hands and into the air? It's all based on how a propeller is shaped. If we look again at the Hughes H-1 airplane, we see that a propeller is like a wing with a twist. Their blades can be twisted at different angles, so that when the propeller or the blades in the propeller begin to rotate, there's going to be faster moving air in front of it and slower moving air behind it. According to Bernoulli's principle, faster moving air is a lower air pressure, while slower moving air is a higher air pressure. So again, when they rotate, that higher air pressure will give it a push from behind or a thrust forward. And that's how a propeller generates thrust.
Okay, thanks again, Jamila. Okay, so let's do a poll question again, shall we? You'll see that come up on your screen. Have you ever blown up a balloon and watched it zoom away? This should be a fairly simple poll question.
And I think you're right. The vast majority of people seem to have had a chance to play with balloons before. And for that 5%, I recommend that you get a hold of one and just run some experiments at home.
Oh yeah, you're missing out there. So in the previous video, Jamila was explaining thrust generated by a piston engine and a propeller. Did you have anything to add to her explanation, Dr. Anderson?
Not really, Mike.
Okay. But she didn't touch upon thrust produced by a jet or rocket engine. So I thought this would be a good image for an explanation of how a jet or rocket engine produce thrust. So could you give us, talk a little bit more about how jet engines and rocket engines produce thrust and how they're somewhat similar in that aspect?
Yes, right. And let's use this diagram to further illustrate here. There we go. Let's go on up to the balloon. Here, imagine, here's a balloon. You blow up the balloon. And let's say that you seal off the neck of the balloon so that there is no air escaping. The air inside the balloon is a little bit higher pressure than the surrounding atmosphere out here. The air inside is a little bit higher pressure because you've blown up the balloon. but it's not escaping the balloon because you have the neck of the balloon closed. Now, we discussed force earlier on in this discussion. The pressure inside the balloon is pressing on the inside surface, exerting a force on the inside surface. Now, in this picture, because there is no air escaping, because the air inside the balloon is just all still and everything is the same, the pressure of the air inside the balloon pressing to the right in this direction is exactly canceled by the pressure pressing in this direction on the left of the balloon, and so there is no net force acting on this balloon. If you just let go of the balloon, it's just going to gradually fall down to the floor. On the other hand, let's say you let go of the neck of the balloon. Here's a picture where suddenly the neck, you've let go of the neck. Now let's look at the pressure inside the balloon pressing on the forward part of the balloon is creating force to the left. The pressure on the inside the balloon exerted on the back of the balloon is creating a force on the towards the right. However, there's this little hole in here where you have opened up the neck. And so this pressure has less area to work on. And therefore, the force pushing towards the right on the inside of the balloon is smaller than the force pushing to the left on the inside of the balloon. The net effect is thrust. There's a forward thrust. You let go of the neck of the balloon, and this balloon starts screaming all over the place because of this forward thrust. Now this is the essence of how a rocket engine creates thrust. Because here, let's go on down to the rocket engine. Inside this rocket engine, we have fuel and oxidizer being burned. There is a pressure distribution exerted all over the internal surface of this engine. The net result of that pressure distribution pushes towards the left. Notice that the the nozzle back here, it's really wide open. There is no material, there is no metal for the pressure to push against back here, and so the pushing is taking place in this direction. The pushing due to the gas pressure exerted on the surface pushes to the left. That's the thrust. That is how thrust is created. Now, what is the effect of the thrust? Imagine that you're the gas inside the engine. You are exerting a force on the walls of the engine. That's creating the thrust. Now, on the other hand, the engine is pushing back on you, the air, and that's pushing you out the back end. That's the reaction. And that is the result of thrust being created, not the cause of the thrust. So the reaction principle here, you have force to the left, you have flow going out to the back, at the back to the right. Newton's third law, equal and opposite reaction. This high-speed jet of air, gas going out the back end, that's the reaction to the generation of thrust inside here. And it's just like this little open neck of the balloon. Since there's an imbalance of pressure force on the inside, the metal pushing on the inside of the rocket engine, that's creating the thrust. And I'll repeat again, if you look at the jet of gas going to the right out here, the gas is out here. If you look at pictures of rocket exhaust, the plumes, they trail sometimes miles behind the rocket engine. And that gas back here isn't touching the rocket. It's having no effect whatsoever on the thrust of the rocket. So once again, the cause of the thrust is the pressure distribution exerted all over the inside surface, pressing to the left. The high-speed jet of air is the reaction to that. The air is being pushed in the opposite direction, but that is the effect of the generation of thrust, not the cause, not the reason for the thrust.
And jet engines work an awful lot like rocket engines, right? They have a flow of air in one direction, basically out the back of the jet engine, correct?
Mike, you're exactly right. It's the same idea. A jet engine kind of looks like this, except you have internal machinery inside. You have a compressor that's compressing the air. You have burners that burn fuel with the air. You have a turbine blade back here, which is taking energy out of the air to turn the compressor. But as you say, the net effect is the flow is in this direction. And once again, the thrust of the jet engine, imagine this now as a jet engine with all this rotating machinery inside here. The thrust is the net effect of all the pressure pushing on the internal metal surfaces, in this case, not just the walls, but the compressor or the turbine blade, which pushes the jet engine forward. It's once again the same idea. The thrust of a jet engine is due to the pressure distribution exerted all over the internal surface, including the compressor blades, including combustion chamber, including the turbine blades, everything that's exposed to that air inside the engine. That is exerting a force which is pushing the engine forward. And this jet of air that goes blasting out the back end of the jet engine, that once again is the reaction to that generation of thrust. It is the effect of the generation of thrust. And it's just kind of a misnomer to say it's this jet of air that's going downstream in the back of the engine that's causing the thrust. Now I'll repeat again, this air that's back here isn't even touching the engine. So how in the world could that be having an effect on the thrust?
Okay, thanks, Dr. Anderson. So I've picked up on what seems to me to be a key concept, and that is pressure difference. You've mentioned it multiple times throughout this online conference. So why is that so important?
Okay, let me start with again the concept of force. Force we talked about earlier is just something you press on with something to make it move, for example. Let's say that you may have a desk in front of you. Let's say you have a book on the desk. If you push on the book, you're going to make it move. Now you have exerted a force on the book. Now what exerted the force on the book? It wasn't you directly, it was your hand. It was the skin on your hand pressing against the surface of the book. And so the book felt a force because of the contact of your hand against the cover of the book. Now the same thing happens when we're talking about airflow over an object. No matter what the object is it airfoil, a wing, can be an arrow flying through the air, whatever it is. How does nature communicate a force to that object? Nature doesn't stand back at some distance, say, let there be a force. Nature presses on the surface of that object by means of the pressure, the air pressure around it, being exerted right at the surface of the object. And so once again, you can visualize, if you're the object, you feel if air is going to exert a force on you, the only way that nature is going to be able to do that is to have that pressure of the air right adjacent to your surface, creating a force on you, pressing against you. Imagine that you're standing outside in a 100-mile-an-hour hurricane wind. Now you're going to really feel an air force. And what are you feeling? If you're standing facing into the wind, you're feeling a high pressure on the front of you, a high pressure. And behind you, the pressure is a little bit lower, so the net effect is a force that's going to topple you over. But again, what's creating that force is the fact that the air is literally in contact with you, and the air that's in front of you in contact with you is at a higher pressure, and the air that is behind you in contact with you is at a lower pressure. The net effect is you're going to be falling over. That's nature's way, nature's mechanism of creating an aerodynamic force. One of the two ways, and let's put it this way, one of the two hands of nature that reaches out and creates an aerodynamic force due to airflow over an object is pressure. The pressure in contact with you. There's a second one that's due to skin friction, due to friction of the air, but we haven't talked about that. Pressure is the dominant thing. You're standing outside in that 100-mile-an-hour wind, and it's that pressure distribution that's going to, pressure difference, going to knock you flat on your back.
Okay. Thanks, Dr. Anderson. Well, I think that's about all the time we have for misconceptions as they relate to lift and thrust. Thank you for participating in the program, and thanks for all your great questions. If you want to find out more about How Things Fly, please visit the How Things Fly website at howthingsfly.si.edu. And if we didn't get to one of your questions, please go to the Ask an Explainer section of the How Things Fly website and submit your question. National Air and Space Museum explainers will work with museum content experts to do their best to answer any additional questions you might have. Thanks again, and Adam, I'll turn it over to you.
Wonderful. Well, I just want to say one more thank you to both of you for joining us. Michael, Dr. Anderson, really fascinating, and you shed light on so many steps of these forces that I think everyone has a lot to work with here. And there were some great conversations unfolding in the chat, and I'd like to throw out another huge thank you to the explainers and educators joining us from the National Air and Space Museum. Some really interesting answers and conversations unfolding there. So if those of you at home missed them, we hope that you'll check out the recording and review what was said there. I'd also like to point out that we've launched an evaluation link in the top left-hand corner of the screen, and we'd love to get your feedback on the session today, so please, before exiting out, click on that yellow evaluation button, and it will launch that in your browser. But until next time, a big thank you for joining us, and take care. Thank you, everyone.